Now let's proceed to rotational symmetry. Rotational symmetry. Rotational symmetry is demonstrated by shapes that have the same appearance on different bases. If we look at our shape here, it's a rectangle, and the rectangle is sitting on the green base. So you see the green side. The green side is the base here, and this is roughly the shape that we're getting. If I flip this, right, such that it's now sitting on the red base, I find that I still get a shape of similar appearance, right? The appearance of the shape here and the shape there is still the same, even though the shape is now sitting on a different side as its base. So when a shape can do that, we say that shape has rotational symmetry. Now, we need now to look at the order of rotational symmetry. The order of rotational symmetry is the number of sides a shape can sit on and produce the same appearance. So if you look at our first shape here, this first shape could sit on two different sides and produce the same appearance. So this shape had an order of rotational symmetry of 2. It had an order of rotational symmetry of 2. Now, for regular polygons, now we said that for a regular polygon, when a shape is regular, it means all sides are equal. For regular polygons, the order of rotational symmetry is equal to number of sides. So if it's 3-sided, order of rotational symmetry is 3. If it's 4-sided, order of rotational symmetry is 4. If it's 5-sided, order of rotational symmetry is 5, and so on and so forth. Provided it's regular, all sides are equal. Now, if you look at a circle is a pretty interesting shape, right? If we try to think of the number of lines of symmetry for a circle, we can cut it like this, we can cut it like this, we can cut it like this, we can cut it like that, as long as it passes through the center, right? So there is, for the number of lines of symmetry for a circle, they're infinite. They're infinite, right? You can't count the number of lines of symmetry for a circle, right? What about the order of rotational symmetry, right? If I roll the circle, it still looks the same, right? No matter what I do, right? So order of rotational symmetry of a circle is also infinite. Because if I roll the circle, it will look the same no matter what. So the order of rotational symmetry is also infinite. Okay, so let's finish off by looking at letters with symmetry, which possess symmetry. So letters with line symmetry are letters that can be cut into two congruent shapes, right? So I took the letters from the alphabet that have line symmetry. So if you look at letter A, we can cut it like that. Letter C, we can cut it like that. Letter D, we can cut it like that. E, we can cut it like that. H, we can cut it that way and that way. I, we can cut it like that. K like that. M like that. O like that and that, T like that. U, it depends. If there's no loop here, we can cut it like that. V, we can cut it like that. W, we can cut it like that. X, we can cut like this and that. Y. So as you can see, all of these letters have line symmetry. They possess line symmetry. Now, letters with rotational symmetry are letters that can be flipped and produce the same appearance, right? So if I flip H upside down, it still looks like in H, it still looks the same. Same thing with I, N, O, S, X, Z. These letters produce the same appearance when rotated. So these are letters with rotational symmetry, and these are letters with line symmetry.